Hello, this is Jennifer Dassinger with A Plus College Ready, and I'm in my third video screencast series of Chemical Bonding to Molecular Geometry and Hybridization of Atomic Orbitals. So let's go into our main concept of Vesper. And Vesper is valence shell electron pair repulsion. That's quite a bit of mouthful. So we just call it Vesper for short. And Vesper basically stands for the predicting of the geometry of the molecules from the electrostatic repulsions between the electrons. And that means between the bonded and the unbonded pairs. It's an arrangement. So molecular geometry is an arrangement in the space of atoms to where you have the different repulsions and the attractions around the nuclei. So molecular shape is the number of bonds plus the number of bonded atoms plus the unbonded atoms to the central atom. So let's just begin and look at some examples. So our first shape is linear. It has a 180-degree example. And the basic class formula that we use is either an AB or an AX. An AX, A stands for central atom, X stands for the bonded atoms, either single, double, or triple, and E stands for unshared pairs. So let's begin and look at our formula. So if you have two bonded atoms, like the oxygen to the carbon, there are no unshared pairs around the carbon. You will have a linear shape, 180-degree angle. And don't forget, carbon dioxide will have two double bonds on either side. The oxygen to the carbon on either side will create a double bond. Let's look at another example of this. So beryllium chloride has beryllium in the center. Now remember, beryllium can only gain up to 4 valence electrons. Beryllium, boron, and hydrogen, BBH, are the 3 examples to the octet rule. So even though you have chlorine and chlorine on either end and they have unshared pairs, it's not on the central atom. And if you look at the polarity, there's a zero dipole moment in terms of the amount of unshared on the left versus the unshared on the right balance each other out. Therefore, it has a zero dipole moment and yes, creates a linear shape and a 180-degree angle. Ready for some more? Let's go to it. So AX3 has 3 atoms bonded to the central atom and 0 unbonded pairs. So boron trifluoride is an example. It creates a trigonal planar shape. And that will have 120-degree angles on all 3 sides. Sounds something familiar, right? Our next category is AB4 or AX4, and that's a tetrahedral shape. And carbon tetrachloride has 4 chlorines attached to the central atom and no unshared pairs around the central atom. And it has a bond angle of 109.5. Our next classification is AB5 or AX5. And phosphorus pentachloride is our example. We have 5 atoms bonded to the central atom with 0 unshared pairs around the central atom. Now notice, it creates a shape called trigonal bipyramidal. Now notice, tri and bi, 3 and 2 make 5. That kind of helps you out a little bit. It also has 2 bond angles, 90 and 120. Our last category in this classification is AX6. And AX6 creates an octahedral shape. And you will have 6 atoms bonded to the central atom, such as our example of sulfur hexafluoride, and no unshared pairs around the central atom. And yes, you will have a 90-degree angle shape all around the central atom. Well, that's one set. Ready for some more? Here's our next set, and we're going to compare and contrast the two. Remember we just talked about trigonal planar, or trigonal planar, either one. Well, we also have what we call a bent structure. And if you notice, the bent structure has an AX2E, and that E represents an unshared pair of electrons. So 10,2 chloride gives us this example. We have an unshared pair around the central atom. Now let's compare tetrahedral to a trigonal pyramidal. Notice the tetrahedral has no unshared pairs, but the trigonal pyramidal has 3 bonded atoms and 1 unshared pair. Our example is phosphorus trichloride. Let's compare a tetrahedral now to another bent structure that we're very comfortable with, and that is water. Remember, water has 2 unshared pairs of electrons? So the example that I also have listed at the bottom and with the GIF, you have the AX2E2. So this will have 2 bonded atoms and 2 unbonded atoms. Just to give you some more examples. Let's compare some more. Remember our trigonal bipyramidal? Well, let's look at what we call a seesaw or distorted tetrahedron. I like seesaw. Reminds me of my elementary school days. So the seesaw shape will have 4 atoms bonded to the central atom and 1 unshared pair. It's unbalanced, hence the name seesaw. Back and forth. Let's compare our trigonal bipyramidal to what we call a T-shape. And a T-shape is where you have AX3, E2. So that means you'll have 3 atoms bonded to the central atom. You have the 3 fluorines with our chlorine trifluoride, and you'll have 2 unshared pairs around the central atom. This is what we call a T-shape. Ready for some more? Here we go. We're going to compare that trigonal bipyramidal to a linear. Yes, a linear. And you're like, what? This can't be linear. But let's talk about it. It's got 2 atoms bonded to the central atom and 3 unshared pairs. So if you look at it, it's evenly and opposite around. So this is an example that has been used on the AP exam in the past as an FRQ. So I just wanted you to practice looking at this. Definitely draw the Lewis structure and see for yourself. But it does have a molecular geometry of a linear shape. And that, don't forget, when you draw the Lewis structure, that negative charge has to be outside the bracket. One more comparison. For now, square pyramidal to an octahedral. So a square pyramidal has 5 atoms bonded to the central atom and 1 unshared pair. Notice a square planar, very much similar to a square pyramidal, will have 4 atoms bonded to the central atom and 2 unshared pairs. So the example I have listed over to the right is xenon tetrafluoride, and it makes that square planar. Down at the bottom, I have the iodine tetrachloride ion, and don't forget, when you draw the Lewis structure, again, that negative ion has to be outside the bracket. Let's continue. Here is the gigantic table of all knowledge. So if you notice, I've got all the categories put together. I wanted to compare and contrast the ones that had no unshared pairs versus the ones that do have unshared pairs to kind of give you that frame of reference. So let's talk dipole moment again. Remember, a dipole moment is where you have an end of your molecule that has more unshared pairs of electrons around the central atom. Now remember, hydrofluoric acid, fluorine, even though it is the most electronegative, hydrogen can never be the central atom. Therefore, it has an extremely high dipole moment. And if you notice the arrow pointing in the direction of the greatest polarity, and that needs to be drawn on your Lewis structures when explaining what is a dipole moment and polarity. So if you notice ammonia, the behavior of these dipole moments will be pulling. So remember, the hydrogen is partially positive, and you've got those three hydrogens pulling into the nitrogen. At the same time, you have the unshared pair of electrons above nitrogen that are negatively charged, and they outweigh those three. So think of a tug of a war. You have three people on one side and a really strong person on the other. I'm sorry, think of a defensive lineman versus three running backs. The defensive lineman, I'm sorry guys, is going to win. You can look at it that way. Little football reference. A result in no dipole is where if you look at nitrogen trifluoride, it has a very small or almost negligible, but still has a dipole moment, a lot less than ammonia, but it still will have a dipole moment, even though those three fluorines are pulling equally and oppositely in every direction. It's going to outweigh that one unshared pair of the nitrogen. So it still has a dipole moment there. So which of the following molecules have a dipole moment? Let's take a look. Look at water. Water has those two unshared pairs. It's going to be pulling them up in that direction. Sulfur dioxide is dipolar because it has that unshared pair on the central atom and it's pulling it down and pulling it out. Oops, excuse me. But now look at methane at the bottom right. Methane has equal and opposite. So there's not one pulling in one direction. So if they're all pulling in the same direction at the same rate, it is a nonpolar molecule and no dipole moment. Remember our friend carbon dioxide? It had two double bonds on either side of the carbon with the oxygens attached, and they have equal polarity to both sides. Therefore, that creates that non-polar molecule or no dipole moment in the molecule. Still confused? Look at the values that are measured. If you compare linear to bent to trigonal pyramidal, you can see that the ones, for example, of hydroiodic acid has the least polarity or dipole moment. Who has the most? Again, our friend hydrofluoric acid has that greatest polarity on that end. Now that we've talked polarity, let's talk about what hybridization is. And hybridization is a mixing of two or more atomic orbitals to make a new set of hybrid orbitals. So remember when you did your electron configuration and orbital notations, and you did the 1s2, the 2s2, the 2p6, etc. Excuse me. Those are going to overlap to form hybrids. And when they overlap, they're going to create that shape. So pause the video, take a moment, and look at the notes. So after you've taken a moment to look at the hybridization points that I've listed here on 1, 2, and 3, notice on 1, two non-equivalent orbitals, such as S and P, will make that different shape. 2, equal to the number pure atomic orbitals are used in hybrid process. And number 3, the overlapping of those atomic orbitals with other hybrid orbitals. Still confused? Let's look at some examples in our next video. So continue on to part 2 of our next video series.